Welcome to the module on flexible pavements. Today we will be discussing about the mixed design of granular sub-base materials. Granular sub-base material is a material which is being generally laid on top of the subgrade, and it is the main load-bearing member of the roads in order to get the stable and durable roads. So what is a granular subbase? If you see in highway engineering, subbase is the layer of aggregate materials laid on top of the subgrade on which the base course layer is located. It may be omitted when there will be only foot traffic on the pavement, but it is necessary for surfaces used by vehicles. Subbase is often the main load-bearing layer of the pavements. Its role is to spread the load evenly over the subgrade. The materials used may be either unbound, granular, or cement-bound materials. The quality of the subbase is very important for the useful life of the roads. As an introductory part, aggregates are used in a granular base and subbase layers below the driving surface layers in both asphalt concrete and the Portland cement concrete or the PQC roads. The granular base layers is directly below the pavement surface and acts as the load-bearing and strengthening component of the pavement structures. The granular subbase forms the lowest bottom layer of the pavement structure and acts as the principal foundation for the subsequent road profiles. It provides drainage for the pavement structures and protects the structure from the frost. The materials which are generally acceptable to be used as granular sub-base materials are aggregates used generally consist of natural materials, sand and gravels, crushed stone or quarry rock, slags or other hard durable materials of mineral origins. Use of materials like brick metals, concrete and crushed concrete shall be permitted in the lower subbase. The term natural materials shall include but not be limited to the gravel, soft stone, sandy soils or a combination of any of these materials. Grading requirements of GSB is given in table 400.1 of MORTH. The extract of this table is being shown in this slide. The gradations are generally divided into 6 types, grading 1, 2, 3, 4, 5 and 6, and the CU sets are ranging from 75 to 53, 26.5, 9.5, 4.75, 2.36, 0.85, which is rarely used in grading 5, and 0.425 or 75 micron CUs. Generally used gradings are grading 5 and grading 3. Upper subbase drainage layers are grading 5 and 6 and lower subbase are grading 3 and 5. Once the grading is met, the aggregates are mixed in the required proportion to achieve the mix. The mix thus formed is tested for various physical properties as given in table 400.2 of MORTH. The physical properties which are required to be met when the material, that is the GSB material, is to be approved for use in construction is water absorption should be less than 2%, CBR at 98% dry density should be more than 30%, liquid limit should not be more than 25%, plasticity index not more than 6%, aggregate impact value should not be more than 40%, and the compaction required is 98% of the maximum dry density which is achieved in the laboratories. The physical requirements of materials, if you see, the water absorption values of the coarse aggregates shall be determined as per IS 2386 part 3. If these values is greater than 2%, the wet aggregate impact values shall be carried out on the materials delivered to site as per IS 5640. Soft aggregates like concretes, brick ballast and laterites shall also be tested for wet AIV as per IS 5640. The materials shall be free from organic or other deleterious constituents and shall conform to the gradings given in table 400.1. If you are using the crushed aggregates for designing the GSB, it can be a round or a crushed aggregates or different sizes can be mixed in required proportions and will be made suitable for meeting the grading requirements given in table 400.1, or you can have the crushers to be adjusted in such a way that the output of the crushing material itself shall meet the grading requirements of a GSB as given in table 400.1. Once the grading is met, the aggregates are mixed in the required proportions to achieve the mix. The mix thus formed is tested for various physical properties as elaborated in table 400.2. Samples is air dried and tested to find the Proctor values using Proctor tools as per IS 2720 part 8 to achieve the maximum dry density and the optimum moisture content. The values of MDD and OMC thus obtained are being used in determining the compaction of the GSB material during the construction phase. When you are using a natural material, again the natural source is available, then the samples are being directly drawn from the source and checked for the grading requirement. It can be now as given in table 400.1 of MORTH specification. Once the grading is fulfilled, then the other physical properties are being checked like AIV, moisture absorption, and then the Proctor values. Proctor value is determined to get the MDD and OMC of the GSB material thus formed and is utilized to get the percentage compaction in the field. If it is a natural material, then it needs to be sieved through the set of sieves or the arrangement as shown. Today we will be discussing about the design of granular sub base, which is an important component in roads. So to start with, the first test which needs to be conducted for the design of granular sub base material is gradation. Now here we have chosen grading 4 of table 400.1 of MORTH, according to which the grading starts at 53 MMCU and then 26.5, and then you have 4.75 CU and thereafter 75 micron CU. The percentage passing on each CU is being noted in the sheet as shown in the figure. The weight retained on each CUs and then the percentage weight retained, which is converted into a percentage cumulative weight retained, and this minus 100 will give you the percentage passing on each CUs. Now the gradation of the GSB material is being done on number of samples. So this is the sample number 1 which is being detailed over here, but to streamline or to finalize the grading, what is required to be done is at least we have to take 5 to 6 samples from different locations of the stock of GSB material and check for the grading requirements. Then once the grading requirement is met, the material is being tested for Proctor test. Now what is done is the same material is being taken to conduct the Proctor test, which is a modified Proctor test as per IS 2720 part 8. Then in this what is required is weight of the mold we have already checked, that is 5730 grams. Volume of the mold is 2250 because it is 150 dia mold, which is a higher diameter mold. Now in the Proctor test, the weight of sample plus mold is being noted down. Weight of wet sample is being calculated. Wet density of the sample is again calculated. Once we know the volume, we know the weight, so weight divided by volume will give you the volume. Since the sample is wet, so that is the reason it is being called as wet density of the samples in grams per cc. Then using the container in the oven dry method, the moisture content of that particular soil sample is to be determined. For that we have to choose the containers. In this particular example we have chosen containers starting from number 1 to number 6. Weight of number 1 container is 77.51 grams, and then weight of wet sample plus the tray is 520, and weight of dry sample plus the tray is 510.16. Between wet and dry samples, the sample is being kept in an oven at 104 0.5 degrees centigrade temperature for 24 hours to get the dry weight. Then the difference will give you the weight of water in grams. Weight of dry sample is 432, so water content will be 2.35, and then dry density is wet density divided by 1 plus water percentage will give you the dry density. So this is how for all the samples the moisture is being calculated, the moisture percentage is being calculated, and in this particular example you can see that for each sample you have an increment of moisture content from 2.35 to 4.15, then 5.12, and then 7.19, 8.43, and 9.09. Now corresponding to the dry density, if you see, the dry density is maximum, as that is 2.217 at a moisture content of 7.19, and thereafter it goes on decreasing from 2.146 to 2.079. So your maximum dry density will be somewhere in this range, which is varying between moisture content is around 7.19 and the dry density is around 2.217. Now to determine the maximum dry density and optimum moisture content, a graph is plotted using the moisture content or the water content in percentage and the dry density. Water content is being taken in the x-axis and the dry density is being taken in the y-axis, and then the plot is being done using the different points of observations, and a smooth curve is trying to be plotted. Now in this particular example, the one which is being there shown in the table is what is actually getting the maximum dry density and the optimum moisture content. So in this particular case, our value is 2.217 is the maximum dry density, and optimum moisture content is 7.19 percentage. Now weight of the rammer used to determine the Proctor mold is 4.89 kgs, and the number of blows are 55 blows, and the mold is being filled in 5 layers for 55 blows in each layer. That is the reason why it is called as the modified Proctor density, which is being done as per IS 2720 part 8, as you can see on the top side. Once the Proctor test is being done, you can check the CBR of the granular sub base materials after 96 hours of soaking, as shown. The MDD for the soil which has been compacted is 2.215, and the moisture content at which the mold is being compacted is 7.214. Now in this particular case, again 3 molds, mold number 16, mold number 17, and mold number 18 are being used. Each mold is being filled with 5 layers, and number of blows are 56. And the condition of the material before the soaking is being noted down, like weight of the mold, weight of the wet material plus mold, weight of the wet material itself is the difference between these two, and then the volume of the mold is 2250, since we have taken a 150 dia mold. Then you have to calculate the wet density of the samples. So the wet density before soaking and wet density after soaking is being noted down for each type of mold. Now as you can see that wet density before soaking is 2.378, and wet density after soaking varies from 2.403 to 2.394, as shown in the table. Now the moisture determination again for before and after soaking is being determined by using a oven method, which is again the sample has to be kept for 24 hours at a temperature of 110.100 at a temperature 104.5 degrees to get the water content in percentage. Now once we get the water content, we get the dry density of the soil sample, which is nothing but the division of wet density divided by the moisture content. So you know the dry density, then the percentage compaction can be determined, which is nothing but D26 by I 17, where I17 is this value 2.215 and 2.217 is your dry density achieved before soaking. So the percentage compaction is 100.09 in this particular mode, or after soaking the percentage compaction is 99.55. Now the idea is this mold after soaking of 96 hours and getting the swelling index also is being tested for penetration test, which is being conducted on the CBR mold and the CBR machine. The proving ring has a calibration factor of 6.45. That means this is the multiplication factor of the readings being checked in the penetration apparatus. Now the rate of loading is 1.25 millimeters per minute for the CBR plunger to penetrate the soil in the machine. The penetration versus load graph has to be find out. So what is being done is for each type of each penetration, that is starting from 0.5, 1, 1.52, 2.54, 5, 7.5, 10 and 12.5. For each penetration, the proving readings were noted down. Now these readings, when multiplied by the correction factor or the calibration factor of 6.45, you get the load in kgs, which is 174.15 for 0.5 millimeter penetrations. Now the load corresponding to 2.5 millimeter penetration is 825.6, which is once divided with a standard load of 1370 will give you the corrected CBR, which is 60.26. And similarly, the load corresponding to penetration of 5 millimeters is being calculated as 1302.90, and this being divided by the standard load, which is 2055, because standard load for 5 millimeter penetration is 2055 and standard load for 2.5 millimeter penetration is 1370. So this is divided by standard load of corresponding penetration value will give you the CBR of that particular mold. Now for corresponding 16, 17 and 18, all these three molds, the CBR values at 2.5 millimeters and 5 millimeters are being checked, which is 62.62 and 66.85 for mold number 17 and 62.15 and 66.23 for mold number 18. Now, if you plot a graph with respect to mold number and the CBR value corresponding to the different penetrations, which is at 2.5 and 5 millimeter penetrations, as shown in the table below, you will come to know that the mold number 16 is having 60.26 and at 2.5 and 5 millimeter penetration you have 63.40. So the average CBR at 5 millimeter penetration works out to be 65.49. CBR value at 2.5 is calculated to be 61.66 and the CBR value at 5 millimeter penetration is 65.49. So the test needs to be repeated, but in the repeat test also we got the same results. So that is the reason why we have taken CBR at 5 millimeter penetration value as the CBR value of this particular soil. Even when you plot a graph, you will get the same values, almost the same values. In the graph also, you have to plot the penetration in the x-axis and you have to take the load in the y-axis and then plot a graph. Now corresponding to 2.5 millimeter penetration, the corresponding value will give you the load in kgs of CBR penetration of 2.5, and corresponding to 5 millimeter penetration you will get the load. Now this load again divided by the standard load will give you the CBR at that penetration. That means, for example, in this particular case at 2.5 you have the CBR of 62.15 and at 5 millimeters you have the CBR corresponding to, which is say 66.23. Similarly, for all the molds, this is being calculated for mold number 18. Similarly, the graphs are being drawn for different molds, that is mold number 17 and mold number 16. And for each mold, from the graph also the CBR values are determined and being put into the chart. Now once you have done with the CBR test, the GSB material needs to be tested for aggregate impact value. Aggregate impact value is again a material is being tested on aggregate impact tester. Weight of sample passing 12.5 and ISUs and retained on 10 mm is being utilized to do the test. Then once it is being crushed with an impact, the weight of fractions retained on 2.36 mm ISU is being noted down. Now the percentage of fraction passing 2.36 mm ISU is being calculated, which is the difference between the initial weight minus the final weight. Now the percentage aggregate impact value in terms of percentage, if you see, that is 52.0 divided by the total weight, that is 318, which is nothing but D11 by D19, works out to be 16.35 for sample number 1, and similarly 18.75 for sample number 2, and the average value is 17.55. Once liquid limit test is being done on GSB material using penetrometer test. This test is being conducted as per IS 2720 part 5. Now in this particular test, what is being done is the penetration is being noted down for different samples, and the corresponding moisture content is being determined, and a graph is plotted between the penetration in the x-axis and the moisture content in the y-axis, and moisture content corresponding to 20 mm penetration is what is known as the liquid limit of this particular soil. Now liquid limit are determined as 21.2, and being a non-plastic soil is being noted as NP in this. The next test which is being required to be conducted is water absorption of the material. The water absorption of GSB material is being done as per IS 2386 part 3 using wire and basket methods. Now under the SHD conditions, weight in air and sample in air and oven dried sample is being checked, and then the difference will give you the water absorption of the materials. Once the water absorption is done, the 10% fines values are being checked as per IS 2386 as per IS 2386 part 4. So again, weight of the soaked sample which is being passed from 12.5 and retained on 10 mm sieve is being taken for the test. Weight of the fraction passing IS 2.36 after the test is being noted down. The weight retained on 2.36 sieve is being noted, and then the percentage passing through 2.36 test is being calculated as W2 divided by W1. That means weight of fraction passing divided by the weight retained in terms of percentage is being noted down. Now force required for 10% fines is 52.4, and the 10% fines value is nothing but 7.94 divided by 52.4 into G plus 1, 14y divided by x plus 4. So here y is the force required for 10% fines, x is the percentage of finers passing through to 2.36 ISU test. So once all the gradings are being freezed and test is being conducted, the average summary is being noted down. So percentage passing on GSB material, the average percentage passing is meeting the requirements specified in grading 4. So this is the average value which is being checked for the grading, and this is the limit as per, this is the limit which is being shown in MORTA, that is at 26.5 required percentage passing is 5280, whereas actual percentage passing is 68.3. At 75 microns use, required percentage passing is 0 to 5, whereas the percentage passing achieved, actual percentage passing achieved is 2.25, hence approved in terms of grading. Water absorption, the value is less than 2%, which is 1.83, hence this material can be used as a GSB material. Aggregate impact value, what we are getting is 17.55, the average value, which is the average of 2 samples. Then Atterbuck's limit 21.5, which is again an average of 2 samples, that is 21.2 and 21.8. Now Proctor test, again 2 samples are being tested. The average MDT value is 2.215 and the average OMC is 7.24 as shown in the table. The CBR value is being tested and found as 65.49 for the GSB material, and 10% fines is 62.45, which is the average of the 2 samples. Now, when you see the mix design summary, it has to be noted down as given in this table, like the specified limits given in MORTH table 400.1, which is corresponding to grading 4 of the material. And the liquid limit maximum allowed is 25, and we are well within the limit. Plasticity index maximum allowed is 6%. Water absorption maximum allowed is 2%, which is again well within the limits. Aggregate impact value is maximum allowed is 40%, and actually achieved is 17.55. The CBR value minimum required is 30%, and we are at 65.49, which is again meeting the requirements. Minimum 50 kN is required, 10% fines value as per IRC 15, which is not a requirement given in MORTH, but as per IRC 15 2017, 10% fines value should be minimum 50 kN, and what we are getting is 62.45. Hence, the materials can be approved for GSB to be utilized in the field. To summarize this module, we talked about the definition of granular sub base, the design of granular sub base materials in specific, and it has been elaborated using the Excel sheets. The materials required for the granular sub base, the specifications given in MORTH as far as the physical requirements of the material is concerned or the grading requirements are concerned.